Okay, carrying on with this this first type of enthalpy problem. So I did the first part there. Now the second part of the problem was if we want to produce 350 kilojoules of heat, how many grams of methanol would be needed? And again, we've got that balanced equation here. We've got the enthalpy there. So in this case, the information we're given with is the quantity of heat we're trying to produce. So we would start with that. 350 kilojoules. Now the kilojoules does give us how we can relate to the enthalpy. So we're talking about methanol, that's CH3OH. 1 mole of methanol reacts, and this reaction would produce 359 kilojoules of heat. So I can put the enthalpy value into my calculation that way. 1 mole of CH3OH would produce 359 kilojoules of heat. Kilojoules cancels out. So we start with energy. We just need to invert our enthalpy, and now we're into quantity. We're asked for grams, so this is molar mass again, but with methanol it'll just be, there's 1 carbon, 1 oxygen, and 4 hydrogens. So 12.01, 16.00, and 4.04. 2 carry the 1, 32.05. So 32.05 grams of methanol is 1 mole of methanol. All our units cancel out there except for grams. So this would tell us how many grams of methanol we would have to react to get that quantity of heat. So 350 divided by 359 times 32.05. We only have 2 sig figs here because of that 0 not being significant, so I'll round this to 2. It would just be 31 grams when rounded to 2 significant figures. So from my perspective, these are pretty straightforward problems, right? You're given the information you need. You're really just working through your units to get to your answer. So keep that in mind. If you see a problem, you see the balanced equation, you see the enthalpy, keep in mind, I'm just going to relate those pieces of information. Now, one thing to watch out for that could make this a little more complicated, right? When we're defining enthalpy, we're really careful about moles and how it relates to the reaction being in the units. That is not common for the way enthalpy is written generally when we're looking at problems or even in the textbook. Because once we've kind of figured out that the stoichiometry is important, enthalpy is often just listed in kilojoules because its relationship to the reaction should be something you understand. So if it's just written as kilojoules, that might make it a little harder to recognize the relationship to moles because it's not as explicitly written in the problem. But if you understand what enthalpy means, you should still be able to make that connection. And then this is really just a unit problem, dimensional analysis. Okay? Now, the second type of enthalpy problem that we'll look at, and in my perspective, these are pretty fun problems to do because it's really like just sort of solving a puzzle. It's called Hess's Law. Excuse me, something's blooming today. Hold on a second. Okay, sorry about that. That's immortalized in the video now. Hess's law states that if a reaction is the sum of 2 or more other reactions, the change in enthalpy for the overall process, right, or the overall reaction, is the sum of the change in enthalpy values for those reactions. Now, the way we can use this is if there's a reaction that's hard to study, you know, an explosion or something, we could put together other reactions and calculate the enthalpy of the reaction we're trying to study by combining the enthalpy values of reactions that are a little easier to measure experimentally. Now, I'm going to go through how we can kind of work through this process, but let's look first at just how this is set up, because again, I mentioned 3 different types of problems. If you're looking at a Hess's Law problem, the most important thing you will see is a target. So calculate the enthalpy change for the following reaction. There's our target reaction. Right? The other thing you will see, given the following, is a bank of known reactions. So Hess's law is describing the fact that we can combine known reactions to get the enthalpy for an unknown reaction. So all of that will appear in the problem. So this is very different from what we saw for the first type of problem. So right off the bat, you should be able to recognize what is at stake in the problem and what you should do to solve it. Now, how do we go about solving a Hess's law problem? I would recommend start with your target and just try to build your target reaction. So if I look at my target reaction, the first thing I need is 2 carbon atoms, and it should be in the solid state. So I'm going to look down here in my bank of known equations for carbon. And here it is. Here's carbon. It's a solid. So that's similar to what I see in the target. It's just not enough. I've only got 1 mole of carbon here. I need 2 moles of carbon. So what I'm going to do is I'm just going to double this equation. So I'm going to rewrite the equations below here. We'll see if I can fit them in. I'm going to double it. If I take 2 carbon atoms, double the amount of oxygen, that could react with 2 oxygens, and that could make 2 carbon dioxides. Right? Now, in the bank, the enthalpy for the reaction that's given is minus 393.5. But if I use twice as much material, there's going to be twice as much of an energy change. So the enthalpy change associated with this new reaction where I have 2 moles of carbon is going to be 2 times minus 393.5 kilojoules. Okay, and I want to keep track of that too if I make a change. Now I'm going to use another color here. 2 carbons is what I started with there. I have now added 2 carbons in my setup to try to cancel out these reactions and make the target reaction I'm looking for. Okay? Next thing in the target is hydrogen. So I've got 1 hydrogen and it is in the gas phase. Here's that in my target, in my table of known reactions. So H2 in my target, here it is in my table. It's 1 mole. It's the gas phase. It's also on the reactant side. So this reaction is perfect. I'm going to use it just as is. 1 mole of H2 plus a half a mole of O2 gives me a mole of water in the liquid phase. Enthalpy, I didn't change the reaction, so nothing changes about the enthalpy. It is exactly the same, 258.5, but it's negative. It's an exothermic reaction. Okay, and there's my second reactant for my target equation. Now the third thing in my target equation is the product here, which is acetylene, C2H2, and I want to find that here in the known reactions as well. And here it is. It is the reactant here in this reaction. Now the moles is right. It's 1 mole up here in my target. It's 1 mole here. That's fine. And the phase is fine as well. It's gas. But I need it to be a product, not a reactant. Well, here's where directionality comes in. If I want this to be a product, I'm just going to flip-flop this reaction. I'm going to take the products, make them the reactants. So if I have 2 moles of CO2 gas, and that reacts with a mole of water in the liquid phase to make 1 mole of acetylene, and that would make 5 halves or 2.5 moles of oxygen. Right? That would provide the missing piece that I need for my target reaction, which is acetylene as a product. Okay? So that would complete my target reaction. Now, if that reaction had a negative enthalpy in the direction it was written in the bank, what if I flip that around, that is going to change the sign. So this is now going to be an endothermic reaction, but it's going to have the same magnitude of enthalpy. It's just going to be positive instead of negative. Now, what I want to think about here is what if I add these 3 reactions together? Right? That's what Hess's law says, is if we can combine reactions and get the reaction we're looking for, then we can combine the enthalpies. Right? So what we need to think about now, the blue underlined species are the ones in my target reaction. There's a whole lot of other stuff here as well, but some of it is going to cancel out. If I combine all these reactions and I have the same thing present as a reactant and a product, it wouldn't appear in the overall equation that describes that reaction. So if we set this up correctly, we should at some point be able to cancel out all of the other pieces. So if you look here, there are 2 moles of CO2 on the reactant side here, and 2 moles of CO2 on the product side here. That means if I combine these 3 reactions, that is not part of it because it hasn't changed from reactant to product in the combined reaction. There's a mole of liquid water on the reactant side and a mole of liquid water on the product side. That also cancels out. Right? And here's 2 moles of oxygen and then another half mole of oxygen, which is 2.5, and 5/2 is also 2.5, just written in a fraction instead of as 2.5. So all the oxygens also cancel out. The only thing left over is exactly what I had in my target reaction. Right? And that is what Hess's law tells us to do. It says if we can combine those equations to make the target reaction we're looking for, then we can combine those enthalpies, and that will be the enthalpy of that target reaction. So if you set it up kind of the way I did, all we need to do is do the math here, combine this. Now we do have to be very careful of the negatives here. So I'm going to start with the 1299.6, and then I can subtract the others. Whoops. 1299.6 minus 258.5, and I hit a wrong button. 1299.6 minus 258.5, okay, and then minus 393.5, but I need to do that twice. Okay, so that leaves me with a positive 254.1 kilojoules. So the enthalpy change for the target reaction here would be plus 254.1 kilojoules. So it would be an endothermic reaction. We would have to add heat. Okay, so this is how Hess's law works, right? It's really like a little puzzle where you're putting all the pieces together to get the reaction you want. We'll do one more example with Hess's law because there's another little wrinkle we want to make sure we're ready for if it pops up. We'll do that in the next video.